All right, hello everyone, and welcome to lesson 5.2 for AP Chemistry, which is on Introduction to Rate Law. Today we are focusing on why some chemical reactions occur quickly while others happen more slowly. Reaction rate is going to depend on factors such as reactant concentration and temperature, and we are going to use experimental data to understand these effects. Our goal is to represent this data using a rate law expression, which shows how the reaction rate is proportional to the concentrations of reactants raised to specific powers. These powers are going to represent the reaction order for each reactant, and if we take the sum of those powers, it's going to give us the overall reaction order. The proportionality constant in the rate law is called the rate constant, which is denoted by a lowercase k. That is going to be temperature dependent and has units that will reflect the overall reaction order. By comparing initial reaction rates, we can experimentally determine the order of each reactant and construct an accurate rate law. A rate law is an equation that describes how the rate of a chemical reaction depends on the concentration of the reactants. Even though a balanced chemical equation shows the overall reaction, it doesn't actually tell us how fast the reaction occurs. Instead, the rate law has a general form where the reaction rate equals a constant K multiplied by the reactant concentrations raised to specific powers. These powers are going to be called reaction orders, and they tell us how strongly each reactant affects the reaction rate. It's important to note that these powers do not come from the balanced chemical equation. They come from experimental data that is collected by observing how changes in concentration affect the reaction rate. Let's break down rate law into its individual parts. So first of all, whenever it's asking you to solve for rate law, you're going to start with the word rate. So rate is equal to K times your concentration of reactants raised to a certain power. The rate is going to tell us how fast the reaction is happening, usually measured as a change in concentration over time. Typically in AP chemistry, you're going to see concentration or molarity per seconds. In our rate law expression, we also have our reactants that are enclosed in brackets. And when something is enclosed in a bracket, we are going to assume that that means concentration, or again, typically molarity. The exponents x and y are called reaction orders, and they describe how strongly each reactant affects the reaction rate. And those values are determined experimentally, not from the balanced chemical equation. And finally, K is our rate constant, which depends on temperature and reflects how likely effective collisions are to occur. Together, all of these terms are going to explain what influences the reaction rate and how sensitive the reaction is to changes in concentration. So before we move on into actually solving for rate law, we need to talk about what reaction order is. So reaction order is going to tell us how sensitive the reaction rate is to changes in concentration. So if we say something is a zero order reaction, that means changing the concentration of the reactant is not going to change the rate at all. So the reaction proceeds at a constant speed and the concentration does not change that. In a first order reaction, the rate is directly proportional to the reactant concentration, meaning if the concentration of that reactant doubles, then the rate is also going to double. In a second order reaction, the rate depends on the square of the reactant concentrations. So if we were to double the concentration, then we are going to quadruple the rate. If we increase the concentration by a factor of 3, then we're going to increase the rate by a factor of 9. So it's just the square of whatever you do to concentration. All right, so what is the rate constant? So its value is going to be different for every reaction and set of conditions. And while reactant concentrations can change during a reaction, the value of a K is going to stay constant as long as the temperature remains the same. Because temperature affects particle energy and collision frequency, when we change the temperature, we're also going to change the value of K. On the AP exam, we are typically being asked to solve for K and identify the units, so it's really important you know how to derive those units for K. Now, when we start doing examples of solving for K, I will show you how to derive the units. However, if you find it easier to just memorize the units for K and you know that the overall reaction order is 2 and you can just write 1 over concentration times time, I'm fine with that, but I'm also going to give you the tools to solve for them as well. And I just want to clarify in this table, this reaction order here is talking about the total reaction order. So we're adding up the exponents. So in the first row here, we have an overall reaction order of 0, which means we only have a 0 order concentration of reactants. In this row here, we have an overall reaction order of 1, which means we just have our single reactant with a power of 1 or first order. Then when we get down to reaction order of 2, that means the total reaction, all of the orders of our reactants is going to be equal to 2. So we're just adding up our exponents. So that can either mean that we only have one reactant with an order of 2, or we have 2 reactants each with an order of 1, and so on and so forth. All right, so how do we actually solve for the rate law? The first thing is you have to have experimental data that is showing your changes in concentration of reactant and your rate of product formation. So here on the bottom of our slide here, you can see that we ran 3 experiments. We have our initial concentrations of A, one of our reactants, and then we have initial concentrations of B, our other reactant. And then finally, we have our rate of formation C. So with this data, we can look at one of our reactants where the other one is constant, and we can see what happens to that concentration and what happens to the rate when that concentration is changed. So let's start out by looking at concentration A. When we are trying to figure out what the order is for concentration A, we have to be looking where B is constant. So we can see that B is constant from experiment 1 to experiment 3. So we are looking at what happens to A from experiment 1 to experiment 3. And we can see that it is tripling. So it is multiplied by 3. Now we're going to do the same thing and look at rate. So when we go from experiment 1 to experiment 3, we are going to have increase by 9. So we know if we are starting with 3 and we are ending with 9, we would have to raise 3 to the second power, which means A is going to be second order. Now let's find the order for our second reactant, which is B. So now if we want to find the order of B, we need to look where A is constant. And we can see A is constant between the first and the second experiment. So looking at B between the first and second experiment, we can see that we are doubling our concentration. And now looking at rate, we are also doubling our rate. So if we have 2 is equal to 2, that means we are raising this to the first power, which means the concentration of B is going to be first order. Now with that information, I can now write my rate law expression. So whenever you are asked to write your rate law expression, you're going to write the word rate. So rate is equal to K, our constant, times the concentration of A, raised to the second power because it's second order, times the concentration of B, raised to the first power because it's first order, or just leave it blank because number 1 is implied. So this would be our rate law expression. All right, so now that we have our rate law expression, which is shown here, we can actually use the data from the table to solve for K. So remember, when you're solving for K, to watch your units. If you plug in your units correctly, you're going to get them after you do all the math. But again, if you just wanted to memorize the units of K depending on what is the overall reaction order, I'm also totally fine with that. So with this specific reaction, remember, if we want to get overall reaction order, we just add up the powers. So that's going to be 2 plus 1. So this overall reaction order is 3, or third order. So let's go ahead and solve for K. So if we are going to reorganize this formula to solve for K, we're going to have K equals the rate divided by the concentration of A squared times the concentration of B. So when you are doing these problems, all you have to do is pick one experiment. It doesn't matter which one, just pick one and plug in those same values. So let's go ahead and choose experiment number 1. So rate is going to be 0.015 concentration per second, or molarity per second. And then our concentration for A is going to be 1 molar squared. And then concentration for B is 1 molar raised to the first power. So you can see that one of our concentration units are going to be canceled out. So we're going to be left with 1 over seconds and 1 over molarity squared. So our units can be written as concentration to the negative second power, because we're bringing that to the numerator. And we also have seconds in the denominator, so that's going to be times seconds to the negative first. And now we can solve for our K. All right, so now let's do that with a real chemical reaction. So A says, what is the reaction order with respect to CO, which means I'm looking where NO3 is constant, which is between experiment 2 and experiment 3. Now I can see I am increasing going from experiment 3 to experiment 2, so that's going to be what I'm looking at. And I can see I'm increasing by a factor of 4. Looking at the rate for that same 2 experiments, I'm also increasing by a factor of 4. So if I'm starting by increasing my concentration by a factor of 4 and my rate also increases by a factor of 4, that means I am first order. Now let's do the same thing with respect to NO3. So when I'm looking for reaction order for NO3, I need to look where CO is constant, which is between experiment 1 and experiment 2. If I go from experiment 2 to experiment 3, my concentration of NO3 doubles and my rate also doubles. So if I'm starting with a factor of 2 for my concentration and I'm ending with a factor of 2 for my rate, that means again I am raising that to the first power, which means this is first order. Now remember, when we're looking for overall reaction order, you're just going to add up the orders of each of your reactants. So we have 1 and 1, which is going to give us an overall second order for our overall reaction. Then we need to write the rate law expression. So this is going to be rate is equal to K times the concentration of our reactant raised to the power of the order, which is 1, and then our concentration of our other reactant, NO3, raised to the power of the order, which is again 1. So now if I wanted to solve for K, I need to reorganize this equation. So then I will have K is equal to rate divided by the concentration of CO times the concentration of NO3. And now I can pick any one of these experiments to use the data to plug into this equation. So let's use experiment 1. So my rate is going to be 1.68 times 10 to the negative second concentration per second, divided by our concentration of CO, which is 0.12 molar, and our concentration of NO3, which is 0.72 molar. So looking at units, I can see that capital M cancels out on the top and the bottom, leaving me with 1 molarity unit in the denominator. So if I bring that up, that means I have M to the -1. I also have seconds in the denominator, so it's going to be times seconds to the -1. And now I can just solve, and I end up getting 0.194, and that is our value of K. So now let's do an actual AP Chemistry FRQ from 2008. It says for the gas phase reaction represented above, the following experimental data were obtained. A says to determine the order of the reaction with respect to reactant A and to justify your answer. So again, if we are looking for the order of reactant A, we need to look where B is constant. So looking at B, we can see we are most constant between experiment 2 and experiment 3. So when looking at A is going from a concentration of 0.03 to a concentration of 0.136, which means that concentration is going to be quadrupled or times 4. Now looking at the rate in that exact same experiment difference, nothing happens for rate. So rate is going to stay the same. And when that happens, that means our order for that reactant is going to be 0 order. So a perfect answer to this question would be that the order is 0 order, and that is because when concentration of B is held constant, our concentration of A quadruples while the rate stays the same, which means that the rate is not dependent on the concentration of A. And you got 1 point earned for the correct order and for the correct justification. Now, part B says determine the order of the reaction with respect to reactant B, which means we are now looking where A is constant. So A is going to be most constant going from experiment 1 to experiment 3. So again, we are going to have a concentration that increases by a factor of 4, and our rate is going to be multiplied by 16. So we can see if we have 4 to begin with and we end up with 16, that means we are raising that 4 to a power of 2, which makes this second order. So you would write something along the lines of the order of the reaction with respect to B is second order, and that is because as concentration of A remains the same, concentration of B is going to quadruple, while our rate is going to be multiplied by 16. So that is going to be second order. And that is also worth 1 point for the correct order and the correct justification. So now it says to write the rate law for the overall reaction. So remember, when it's ever asking us for rate law, we're going to start with the word rate. Rate is equal to K times the concentration of our reactant raised to the power of the order. We found that A had a 0 order, and then concentration of B raised to the order, which we found out was second order. Now, as you can see, this is raised to the 0 power, which is going to mean it doesn't actually count towards any of the calculations. So you don't actually write it in your rate law. So our actual final answer is going to be rate equals K times the concentration of B squared. And then part D says to determine the value of the rate constant K for the reaction and to include units with your answer. So we already found that rate is equal to K times the concentration of B squared. So again, we're just going to pick an experiment and use that information to plug it in to solve for K. So let's go ahead and pick experiment 1. So if we're solving for K, that's going to be rate is divided by concentration of B squared. So for our rate, we have 6.67 times 10 to the negative 4th concentration per second. And then for B, concentration of B, we have 0.034, and that is concentration squared. So we end up getting 0.0196, and we can see that one of our molarities is canceled out, so we're only left with one molarity in the denominator. So that means we have m to the negative first times seconds to the negative first, and that is our value for K. And that completes our video for lesson 5.2. I hope you have a great day.